Okay, so I only had one request yesterday of what to cover. It's dynamic programming. So let's look at some of the problems, such as Welcome to CodeJam. And I'm gonna first solve the easy version. So okay, that didn't work. Okay, so the easy version, we get some number of test cases, and each test case is one line containing a string, and we're supposed to say, or we're supposed to count the number of ways we can select a subsequence of some characters that results in Welcome to CodeJam, including the spaces. So you want exactly this string. Yep, I'll do it in Python. No problem. Let's see. Okay, so let's start with input. And then we'll talk about how to solve this. So this should be an integer, and then we read n lines for each test case. That's everything, right? Okay, and then suppose we call some function to count here. So we say the count is equal to something here, x, to some function, and then we print I need to know the test case number. Okay, so let's say for t in range n, and I need 3 leading zeros. String of count. So we want this modulo 10,000, so we only get 4 digits at most. And then while this is shorter than 4 digits, we add a 0 at the front. And we want the test case number, which is t+1, and then the string we created. Okay, so, oops. So how do we go about solving this? So we want to select some subsequence here. And we could use the combinations function in Python to select the subsequence. So essentially we're just selecting a subset of size 19. You have the indices from 0 to 18 here. Stack a letref, yeah, I think so. Yeah, so we could use the combinations function, but if we calculate how many sets we look at in total, you can see the text we have is of length at most 30. So we would have 30 choose 19 sets to look at. And if we just quickly 30 choose 19, we see that's 54 million. But we also have to consider that there are 100 test cases per input. So we have 100 times 30 choose 19, and then divided by 10 to the power of 8. So that's 54 seconds, approximately. And even then we have to iterate through all these sets, so actually there's an additional 19 here. So it's 1000. So here we can apply.
Where does the 19 come from?
Iterating through the selected subset.
Oh, yes.
Yeah, so here backtracking is very useful. And the reason it's very useful is because we can determine the first character. And if the first character is bad, then the entire rest of the selection we could make for that subsequence is also bad. So we can just quit instantly. For example, if we were to select E as our first character, then we know that nothing good will come out of it instantly. So that way we prune out a lot of unnecessary checks. So with backtracking, we can select the first character, make sure it has to be the correct one, and then move on to the next slot. And then we either take it or leave it. So let's define our backtrack function. It'll take, so we need to know where we are in the text, like what position we're at here in this text. And we need to know what position we're at in the the input here, the pattern we're searching for. Welcome to CodeJam. So let's start by defining our pattern. Welcome to CodeJam. And I'll have two variables here, s@, which is for string at, and p@, which is pattern at. Okay, so let's first check for the base case. So the base case is if we have reached the end of both strings, then we have found a valid subsequence. So if SAT equals, here we have to know the length of the string we're looking at. So we also have to have here the text you're working with. So text. So if this is len of text, then we have two cases. We are at the end of the pattern and have found a good subset, or we're not at the end of the pattern and we're out of letters to add to it. So then we can return 1 if path is equal to len of pattern, otherwise 0. So here we are only counting the subsets where we have exactly 19 characters. Okay, and then here we can check if we should try taking the current character. So it has to be equal to the character in the pattern, which we're looking for. So we check if text of SAT is equal to pattern pat. Then we want to call this function recursively. So we can take the character by moving to the next character in the text and moving to the next character in the pattern. Okay, we have to store this result somewhere. So we'll have a sum variable. We'll add that to our sum variable. Okay, but we can also try not taking the character, and then we don't move in the pattern. And then at the end, after summing this up, we have all possibilities. So we can just return the sum. And let me add another function. Count of text, or no. And that will set text equal to line. And I'll have to make this global here, so I can reference this and edit it. And then we just want to return bt of 0, 0. Then we can call count here with line. And I'll have to save this somewhere. Let's just start with the first one here. Okay, it's counting this correctly. Next one. Counted that correctly as well. And this one worked as well. Okay, so before we continue, are there any questions? Is it clear that this counts all the possible valid subsequences?
Yep.
Great. So let's notice one thing here. What we're doing here is we're tracking where we're at in the text and then in the pattern. Now we could reach the same state in multiple ways, but if we reach the same state twice, then why do we recalculate it? It's just a waste of time. So let's store the result based on these values. Let's just make a dictionary. And after our base case, we check if the state is in the dictionary, then return the calculated value. And at the end, if we had to calculate the value, then set the value of this state equal to the result. Here we have to be careful because we're doing different strings each time. So we have to make sure to clear our memory each time we count. So I'll add global mem and we'll set mem equal to a fresh dictionary each time. Okay. So let's test if this broke something. Always do that after you add the memorization. Test if you're getting the same results as before. So here we get the same results as before. Okay, so let's just first try submitting on the easy version. We're using Python 3. Oh, runtime error. That's not good. How do we get runtime error? Ah, of course. We didn't check if we went out of range. Yeah. So here we have to make sure that we check if path is less than len of pattern beforehand. So if you already filled the subset at this point, we don't want to try to match more characters. Okay. So the only difference here is the size, and after memoizing, this shouldn't be a problem because we're doing constant work per state, and there's at most 19 times 500 states, and then 100 test cases. So in total, that's going to be 19 times 500 times 100 divided by 10 to the power of 8. So that's way under a second. Oops, I submitted C++. Okay, so this worked out fine. Let's see. So most people did heritage and atlas. Okay, let's look at narrow art gallery. Okay, so in this problem we have n rows, and in each row we have 2 rooms. So two columns and rows, and we want to close off k of these rooms. So here we're closing off 5 rooms, so that there is still a path from the bottom to the top. So we're not allowed to block 2 rooms in the same row, and we're not allowed to block a left room here and then a right room in the next row. or a right room and then a left room. Okay, so what we have to notice here is that when we make a decision about a room or about a row here, the only thing we depend on is what decision we made in the last row before it and where we are at, and then also how many rooms we have left to close. So you could try greedily doing something here, always closing the minimum one. That's not gonna work. But if you just go through the rows in increasing order, so just go from the bottom to the top, and at each step you have to make a decision with some limited amount of information. It is enough for you to know where you are, how many rooms you have left to close, and finally what decision you made in the last row. The reason you need to know what decision you made in the last row is if you close the left room in the last row, then you're not allowed to close the right room here. If you close the right room in the last row, you're not allowed to close the left room here. If you close nothing, then you're allowed to do whatever. You can not close, you can close the right, close the left. Okay, so can we make a recursive function to try all this? Um, so here we're given multiple problem instances, and each problem instance will begin with a line containing 2 integers and k. Okay, and then 0, 0 will follow the last gallery. So let's just do this simple way, while true, and nk equals the characters on the first line. And then we have all the rows. So we have A, which will be our array. It will be an empty list at first, and then I in range n. We will read into this. So let's just say a dot append, and then tuple split the input, convert to integers, and then make it a tuple. And I need to define these values outside here because I'm gonna use them in my function. So nka equals 0, 0, and the empty list. And then here I wanted to check if n equals 0 and k equals 0, then we break. Okay, so we have our input. Let's make a function. I'm gonna call it calc. So we're gonna start at index 0. We're gonna go through the indices in increasing order, and at each step we're gonna make a decision, which will take us to another state. So here we're gonna need at for the row we're at. We're gonna need remaining, I'll call it the rem, and we're also gonna need what we did last, so last move. So let's go over our base cases. Here we wanted to return the maximum value of the rooms that are not closed, so the sum here. So our base case should be 0 if it's good, because then it has no effect on our sum, but allows us to sum the rest up. The rest of the values here, which we select, without changing the result. Okay, so what's good is when we are at the end, so if at is equal to n, then we want to return 0 if if rem is equal to 0. Otherwise, we want to return some error value, because if we have any rooms remaining to close, then we haven't fulfilled, we haven't really solved the problem. So we'll have some small number here, let's say -1 million. I think that suffices. So if we calculate the value of v times n times 2. So suppose we don't have to close any room, we can just take everything here. This has to still be less than 0 after we sum it up with the values of the room. So that's 20,000 times 2. So this should suffice. Okay. Also, if remaining is no, we don't need any more base cases, I think. Yeah, this should be sufficient. So if we have any rooms left to close, so if rem is greater than 0, then we could either close the left room or the right room. Let's also define our moves. So let's have neither equals 0, left equals 1, and right equals 2. So these are the values this last move variable can take. Okay, so when can we close the left room? It is when the last move was closing neither, or the last move was closing the left room. So if last move is not equal to right, then we can try close left. Also, if last move was not equal to left, then we can try close right. And then finally, we can also, before doing all this, we can try close neither. Okay, so let's store the best answer we have so far. Call it max. So let's try closing neither. So that would be the sum of the two values in our current row. So it would be a at 0 plus a at 1 plus calc of at plus 1, moving up in the next row. We didn't close any room, so we have the same number remaining, and we closed neither. Okay, so we tried closing neither, and now let's try closing left. So we say max is the max of max, and if we're closing the left, then we only get the right value. So that's a at 1 plus calc of at plus 1, rem minus 1, and left. Same for right. So now we only take the left value and we close the right. And then finally we want to return the max we found. Okay, so here we want to did I forget to close something? Yeah, I forgot to close this too. Okay, so here we want to print the value of calc. So we start at row 0. And how many do we have remaining? We have k remaining. And then finally, okay, what was our last move? So the thing that allows us to do everything is if the last move was neither. So we'll just start with that. I forgot the parentheses here. 17. Okay, good. also 17. And 102. Okay, so we're making the correct moves. But this is exponential because we make 3 moves at most. So this is gonna be O of 3 to the power of n, worst case. Or at least O of 2 to the power of n. Sometimes we can only make 2 moves. Sometimes only 1. So how do we make it fast? Well, we use memorization. We store results. So let's define our memory. Then if at rem last move is in the memory, return the result which is stored. And here save the result. And again, let's test if we get the same results. Wait, one thing I forgot. We need to clear the memory between each step. So here set mem equal to the empty dictionary. And that should be enough. To get 102. $17 and 17. Okay. So the time complexity here is going to be the number of states times the work we do in each state. We only do constant work in each state, and the number of states was at most 200 times 200 times these 3 values here. So how much is that? 200 times 200 times 3 divided by 10 to the power of 8. So that's gonna be way, way, way less than a second. But of course there are multiple inputs, they don't specify how many. So if we just divide this by 1 then, no, divide 1 by this all, we could handle 833 test cases like this. Since each of them takes this amount of time. Yeah, any questions? Any more dynamic programming you'd like me to review, or is there anything else you want to review specifically? Did someone say something?
I mean, Only thing I guess would be like maybe a dynamic programming problem I haven't solved. Then I mean, yeah, just sort of see how,
Okay.
given a different problem, how you formulate it.
Yeah. Let me try to find something. Mm, 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 mm. Wow, there are a lot of dynamic programming problems on Catus. I'm gonna try to find something that isn't way too complicated. Mm, mm, mm. Maybe we can go over this one. Okay, so if I'm understanding this correctly, then at each step we're deciding whether we go up or down, and we want to minimize the maximum point we're at. So, like the sample given here, the reason we take up, down over up, down is if we go up, then this takes us up to 40, and then we go down, and end up at ground level. So we need to end at 0 as well. But if we go up, down, then this takes us max up to 20. So the other test case, they say up, down, down. So there they go up by 3, up by 2, down by 5, going back on the ground level, and then up by 3, down by 1, down by 2. Okay, so we have to know at every step, first of all, where we're at, and also what the max building we've seen so far is. Not only. Yeah. So suppose we know the location we're at and the max building, like the max height we've been at. No, not the max height we've been at. We want to minimize that, so that should be our answer. So what we need to know is where we are. How high up are we? Yeah. Because we need to know how high up we are so we can make decisions. Because we need to be able to check if we can take the down step. Because we're not allowed to shoot past ground level. So Yeah, so we need to know where we're at and what height we're at. And then what we want to minimize is the max height will be at through some path of up and down. Um, They say for any scenario, the total distance climbed, the sum of the distances in that scenario is at most 1000. Okay, and then we have n is at most 101. Oh, that's the number of test scenarios. M is the number of distances. Okay. So our state would be, or our state space would be the number of distances. So that's the value of the at variable, where we're at. And then how many values the height variable can take. Well, that's going to be at most 1000. So the least is 0. So that's 1001. And then 101 test cases. So we have 101 test cases times 40 distances times 1001 heights divided by 10 to the power of 8. Okay, so this would be fast enough. Assuming everything we do inside is constant, of course. So let me open up a new file. Um, so let's handle input first. So we have n test cases. And then for each test case, read the number m. And then our array is gonna be this. And then we want to find the path. Okay. So we need to reconstruct the path. So we had a lot of time, right? It was 101 times 40 times 1001 divided by 10 to the power 8. Yeah, we have plenty of time. How much is the time limit? 1 second. Okay, should be fine. Okay, so what we're gonna do here is we're gonna store both the minimum height as well as the path that we took, which gives that minimum height. So we're gonna store two values in the result. So the answer we would be getting for example, the first test case out of our function should be 20 and ud. We get this tuple here. And then at intermediate steps, we may have something like, so if we're at the end, for example, we might have something like just this. Or this. And then from there we came from height 20 and we took a down step to get there. So we're kind of building up the string along the way in our dynamic programming function. Yeah, so we would be calling print of our function calc, starting at 0 and height 0, and then we want the string associated with the value. Oh, but we have to. It's sometimes impossible. Okay, so there's no legal solution. Okay, so we need some value infinity, something that's bad because we're minimizing. So let's say infinity is something like this. Yeah. And then we have to say answer equals this. Or like min result and answer if min result equals infinity, we print impossible. Otherwise, we print answer. Okay, so for our function, well, we need to have the m variable here and also the a variable. Okay, so the location we're at and our current height. Okay, so base case, we are at the end and we are at ground level. That's good. So if at is equal to m, we return 0 because we're at ground level. If we're at ground level. So if height equals 0. Otherwise, we want to return infinity. Okay, and then here we have two choices. So we either go up or we go down. So let's just store these in A and B. So let's say A and B equal infinity first, both of them. And then, okay, we can always go up. Well, let's go up and down. Just, okay, so up is gonna be equal to calling our function for the next value and increasing the height by the position we're at. So a of at. Okay. However, down, we can't always go down. So we have to check if height is greater than or equal to a of at then we can say down is equal to calc of at plus 1 height minus a at. Okay, so we need to track the maximum height we've been at. So the height we're currently at is height, and then the maximum we've been at after that is the first value in up or first value in down. The first value in the tuple. So we have to make a new tuple. So we'll say up is equal to the max of the current value of up and our current height, and then so we're taking an up step here, so the new string here would be u plus actually, let's wait with the string. Let's just do the numbers first. See if we get the correct numbers. And then down is gonna be max of down and height. And then the answer is just gonna be minimum of these two. So either it's better to go up or down. So it's min of up and down. So let's go through this one more time. We are at this position in this height. If we're at the end, so we've done processing all these distances, then everything that didn't end at ground level is bad, so we return infinity in that case. Otherwise, we return 0, because at each step we're taking the maximum here. And of the two maximums, we want the one that gives the lower result. So 0 is our starting point. You start by setting infinity to up and down, and then we can always go up, but we can't always go down. So we calculate the value of up, and then if possible, we calculate the value of down. This is only possible when our height is greater than or equal to the distance we want to go down. Then if the height we're currently at is larger than the max height we've been at the from up or down, so anything at plus 1 or later, then we need to increase the max value to what we're at right now. And then the answer is just going to be the minimum of these two values. So we can return answer. Yeah. Oh yeah, we're skipping the string for now, so let's just print min result. 20, 20, 20, 20. So the highest we go is 20. Okay. 3, 2, 5. 3, 1, 2. And the answer here was up, up, down, down. So the highest we go is 5. We go 3, 5, 0, 3, 2, and 0. Okay, 5, good. And then we're supposed to get impossible. So 3, 4, 2, 1, 6, 4, 5. Okay, great. Now to get the path, we can add the string into the answer. So here we're going to return a string as well. So in the base case, we'll have the empty string, because we don't take any more actions here. Same with infinity. And then when we construct our answer here, we update it. We need to add the step we took to the string. So here we went up, so it's going to be u plus the second value of the tuple. And here we only take the max of the first value. Same with down, max of the first value and the height, and then d plus the string that was already there. And then the answer is still going to be the minimum of the two, because we're taking a minimum of a tuple. So first it will compare the first two values, so the first value of up and the first value of down, and then it'll compare the strings. So the strings only get compared if they are equal, and then we get the lexicographically minimum one. So here we have to get the answer and print that instead. I must have forgotten something. Down. Ah, yeah, here. No, wait, what? This is our base case. Another base case. Right, here. Yeah. So this has to be like this as well. Okay, then we have the strings as well. Alright, so this is gonna be too slow at the moment, so what we have to do is just memwise the state. So we'll have mem, and we have to remember to reset the memory at each step. So here we check if at height in mem, then return mem of at height, and mem of at height equals answer. Yeah, so this seems correct. Let's try submitting. Right, it worked out. We're a bit close to the 1 second mark because we're using Python, and we're reconstructing the strings at the same time instead of just the single string that we want at the end. So did that help, James?
Yes, definitely.
Okay. Then someone said something from problem solving paradigms. Well, we did welcome to Code Jam with the backtracking and other dynamic programming. You say like the one is. Why did I pick that problem? Okay, so Dvonis was a mistake. I thought the solution was simpler at first, and then realized later in the morning that it wasn't. It was actually more difficult. But we can take a look at it. Okay, so we have some number of elements, and we say that a sequence of 2k elements is interesting if neither the sum of the first k elements nor the sum of the last k elements is greater than s. And we want to, for each index, we want to know what's the length of the longest interesting subsequence starting with that element. So if we look here, they say the answer is 4. So if we start at index 0, we can take 4 values and this will be interesting. That's because S is 10,000. We can't take 5 because that's an odd number. So 4 is going to be the best one. So here we have the sum is 2 and the sum is 2. So I think the best way to approach this problem is start by simplifying it. Imagine we're only looking for k. We're looking for interesting sequences, but we'll redefine it so that there are k elements, not 2k, and the sum has to be less than or equal to s. Okay, then what we can do is we can build a prefix sum, and for each starting point we can binary search where the largest what's the largest subsequence which fulfills this. So for here we might try, for instance, we start with 0, we try 3, we see, okay, that's less than or equal to 10,000, so we make it larger. We try 4, that's less than or equal to 10,000, and then we try 5, which is also less than or equal to 10,000, so 5 is the best we could do. Now you might think, okay, it works to binary search from start for the chains in this problem. So if we're only looking for k elements whose sum is less than or equal to s, and then you might think, okay, does this work for 2k elements where we split it into halves and each of those has to be less than or equal to s? And it's not, like, I don't see why it would work, but I don't have a counterexample for why it wouldn't. I tried for a really long time to find a counterexample because it was the first thing I tried and it failed. But I wasn't convinced it was correct either. But what can definitely work is so we have these two sequences and they have a center point. So for example, the one we said started at index 0. The longest one was this one. So the first half ends here and the second half begins here. So this is the center. So you could do this binary search for each of the halves. So you binary search from here and from here. In this case, you binary search backwards. So backwards in the list, and here you binary search forward. And whichever sequence is shorter is going to define how the two halves can work together. So if one of them is of length 3 and the other of is length 5, then k is going to be 3, and then 2k is going to be 6. And then what you want to do is you want to do this binary search at every possible center, and then for each center you have to so for example, if we're at here, we say this is our center, and we do this binary search forwards, we get 3 here, and then we binary search from this index backwards and we get 2. Okay, so we know k is 2 now. So we need to find, okay, if this is our center, then where does this sequence start? And since k is 2, then it's just this index minus 2. It started here. And then after collecting all these indices, you need to iterate through the indices, and you kind of have to keep track of what's the maximum center you can reach. Or like what's the maximum k you can reach from this point? Yeah, so let's just look at the code here. So we have the range sum here. If a is 0, then it's just the value in the array at index b. Otherwise, we subtract the value at a minus 1 from the value at index b. So here I define some predicates for our binary search. This is for the right half, and this is for the left half here. So you see I give in an index and a value k, which is the size we're checking. And I check if the range sum from index up to index plus k minus 1, so it's a subsequence of size, or substring of size k, if that's less than or equal to s. And then similarly on the other side, I go from index minus k plus 1 to index. So if I'm checking the longest interesting sequence with center index, I first binary search for the right half. So this index here is the center, but the one on the right. So I binary search with the predicate the index I'm at and the mid value I'm trying right now. If the predicate is true, then the best value I find so far is this mid value, and I try to increase k. And if it fails, decrease k. Similarly for the left side, but now we have to note that we were using the right more center index. So here we binary search from index -1 with size mid, and it's just the same thing, but for the left half. And then whichever of these is smaller gives us the value of k. So we return the minimum of the two. Yeah, so here like I said, we keep track of, okay, for the starting index, I minus longest, we push back this I. So we're trying the center I here, and the longest entry in subsequence, we can subtract k to get the starting point of that subsequence. And so for that starting point, we store the center it could reach. And some starting points may get multiple centers. So we need to store this as a vector. And then here what we do is we want to be able to get the max value we have so far. So the max center we can reach at the moment. So we're iterating through the indices in increasing order, and we add to our multiset here. We add each of the values which our current index could reach. So then we're going to take the highest center we can reach and subtract the index we're at from that, and then that's our k, so we output 2 times that. And this is just removing everything that's too little to have an impact. It's unnecessary, but it's just a tiny optimization for speed. But it's unnecessary nonetheless. It's good to remove so you don't have get some value here which is less than I, and then you subtract I from that and get a negative number. So it's good to get rid of it that way by just erasing everything that is too small. But yeah, I thought the problem was simpler. I thought it was just the binary search method I introduced for. So I thought the problem was just k, just a sequence of k elements, and it's not split. It's split into these halves. Maybe this problem is a good example of mixing these things, working with data structures, the binary search method, and also this custom data structure prefix sum. So we're working with all of these here. Yeah, so I posted on Piazza yesterday about the exam. It's split into 5 groups. The first group is gonna account for 30%. It should be the easiest problems. Then we have 4 other groups which each count for 20%. If you get more than 100%, then you only get 100%. If you, for some reason, can't make it to the exam on the listed time, 10 to 2, then let me know. Maybe you have work or something. We can work it out.
Are there any other people that would like maybe, because I would like, it would be nice to have it a bit later. I don't know, maybe it's too late to mention this.
It's kind of late now.
As just wondering if there were like a clear consensus, but never mind.
I mean, I would like it to be later, but we gotta make use
Then
of
we
the
had
time.
In here.
So the schedule was made according to the course being taught locally at school. Yeah, I also want to mention. So in the general channel, Bjarki was posting quite a long message about the organization here, which we have, the competitive programming organization in Iceland. Yeah, and just what the work we do here, and as well talking about the Northwestern European regional contest for the International Collegiate Programming Contest. Wow, that's a mouthful. And we are organizing the contest this year in Iceland. So it will be at Reykjavik University this year and the next year. So if you do not intend to compete, then I'd like to ask you to assist us in setting up everything. We need volunteers for all kinds of jobs. And then he also plugged in an advertisement for a sponsor. So I'd like to ask you to read this, and then if you're interested, please sign up. Now, is there anything else you want to review?
Can you tell us how many problems are in each set, more or less?
Did I forget to write that in Piazza?
I might have read it and forgot about it.
You mean the groups in the exam, right?
How many are in each group, more or less?
2 in every group, I think, except maybe 3 in the first one. But you only need to solve 1 problem per group. So
That I got.
Yeah.
Just wondering how many, like.
Yeah, I'm not gonna overload it so you have to spend all the time reading.
Yeah.
No, it's gonna be 2 problems, so you just have a choice essentially.
Yeah.
And of course, part of the problem-solving process is to find the simplest problem to solve. So you can exercise that as well at the exam. You can, like, maybe one of the problems is harder than the others, so you would like to go for the easier one, the simpler one.
So is the test basically like a problem session except solo?
Um, well, yes, but uh, I'm not gonna have a scoreboard, so it's gonna be like a problem set, and you're solo. Yeah.
Okay.
There won't be a scoreboard, mainly because the scoreboard would impact the way you solve the problem. Probably you would see someone solving, like if you would start solving the problem that's most solved, and we kind of want to exclude that here in the exam.
Are groups 2, 3, 4, and 5 supposed to be, equally difficult?
It's hard to assess difficulty unless it's like the ad hoc problems usually. Um, but the group should be approximately in increasing difficulty order. Just approximately. I can't guarantee anything. Something I find easy, you guys might find extremely hard, and something I find hard, you might find simple. But I'll try to have it in approximately increasing order difficulty. And of course, there won't be any problems from the strings or geometry sets. Uh, it'll be the other 10. Okay, so that's it for today then.